Thank you very much. This talk was meant to be joint with Charisma. Unfortunately, she could not be here today. She's the actual expert on transport modeling, not me. Given that she cannot be here today, I'll mostly talk about my own work, but it has benefited from her input and everybody who's been participating in the group. So without further ado, let me explain what I want to talk about today. So here in transport modeling, there are many questions, but let me make it focused on what happens to passenger behavior when there is an infrastructure change. So change here can be thought in many ways, but it's a type of intervention, so to speak, because you change the way a system works. So you can think in different ways this can take place. You can think in terms of changes that will have a short-term impact or long-term impact, changes which are planned against changes which are just accidents, they are shocks to the system. What I will focus here is in this very particular scenario where the transport system itself is an underground network, in this case, the London Underground, and the type of intervention is unplanned partial line closure. So in the graph that you see here is part of the London Underground map. You see the Victoria and Brixton stations highlighted, and there was an actual event where the Victoria line, this pale blue line that you see there, was not working for a period of time during peak time. So you want to see how this affects passenger behavior, using as information for that data that you have about smart card usage and the actual disruption logs that TfL, that Transport for London, recorded indicating what the problem was. And there are, of course, many ways of measuring passenger behavior for the sake of making things concrete. Here, you looked at the number of exits at different stations during the time the shock took place. So it's the number of tap-outs people do when exiting a station like Victoria or Brixton or other stations in this system. So the main point here is because of the disruption, there may be small changes or big changes to behavior. These here are examples for a different disruption. So this is something that took place for only 20 minutes. And what you see there, these plots represent the usual distribution of the cumulative number of exits during that period in a normal day. You're going to see a little black star in these plots. It indicates the number of exits at that time during the particular disruption. So as you can see there, they're typically on tails of this distribution, and really unlikely events under the natural regime, under the business as usual behavior of the system. And I'd like to be able to understand where this black dot, so to speak, would be if a disruption takes place, because this type of prediction can be used in many different ways. Two particular ways, these are just examples, is once you predict that there'll be some disruption, once you establish there'll be some disruption for at least some period of time, you may want to understand how many people did not reach their destinations, or they went to a different destination than the one they would typically go to, because this is a type of unmet demand of the transport system. So this may have ripple effects elsewhere, people booking more taxis or people crowding buses and so on. And from a more general perspective, in terms of just safety regulations, they wanted to understand, at least drawing particular scenarios, particular hypothetical scenarios, whether some stations are at the risk of overcrowding, depending on the type of disruption that actually happens. Okay, so this is the problem setup. The way you're going to approach here is starting from the basic causal prediction framework. We have some treatment, we have some outcome, we have some confounders that will add to the association but don't correspond to cause effects. And among these confounders, you may have particular covariates that will modify the effect, which might be available to you at prediction time, so you may want to do condition on them. And one way of phrasing the problem is, as you see in this equation, is how the probability of the outcome changes under an intervention of the treatment variable. I use this notation do treatment there as another alternative to say this has been controlled externally, and perhaps some extra covariates that you just observe, you don't intervene on them. Now, in the standard problems like those I've seen Carl speaking, Neil speaking, you may have a very particular treatment variable, a very particular outcome variable. You may have multiple data points that you can use to estimate a response model. But here in this setup, we may have something a bit more complex because we have a whole complex system. We have different stations connected by different lines. Treatment here is not just a single variable taking different values. It's a set of different things which has changed. You may have different combinations of the network which have been affected. It doesn't really correspond to a fixed vector of changes in a multivariate distribution. It's more structured. It's a whole sequence of connections in the network where they're being shut down. In the same way, you can think of your outcome variables varying from event to event because most of the system is not going to be affected. So you may want to focus on only a few stations that will be significantly affected by any disruption. But those may vary from event to event. So you wanted to relate the effects of some intervention or some external shock, not only over different instances of treatment outcome, but actually over different definitions of these treatment outcomes might be. So you need some extra source of structure there in your problem. But at the end of the day, you're going to just take a lift on the general setup. As I mentioned to you, you can create a counterfactual model that relates outcomes on the different interventions. But because you're treating here different variables, both at the treatment and the outcome representation, you may still think those are going to be different response models, but at some higher level, they need to share parameters. So I'm able to say something about what happens under novel disruption, given historical data about different disruptions. So at some level, I need to have some sort of parameter sharing for this out-of-sample prediction to take place. Now, on the other hand, there'll be things that will simplify our life. So in this case, you can just take the shocks as something that has been randomized by nature, so to speak, a type of natural experiment. So you can think of this using medical parlance as intention to treat problem, because you're not really concerned about some intermediate treatment that you did not manipulate. But you do have to worry on how we are going to structure your parameter sharing, which kind of structures we'll have, so these predictions are reasonably accurate. So if you look at people normally do when they're actually going down to the details, writing the mathematical model of these relationships between treatments and effects, we have something like this top equation there. So suppose a treatment is binary, and one classical way of parameterizing the response Y on the variability on your treatment level is to have some sort of default regime. So let's say X equals 0 is a default action. Let's say don't take a drug. So you're going to represent the change so you're going to represent the expectation of the outcome with some function F that depends on the other covariates. And when you wanted to model what happens under X equals 1, you're not going to start from scratch. You're going to just model the contrast, which is represented there by this G of Z. So this dates back at least to classical experimental design. One of the reasons why this is a nice way of representing a response is that your response may be dependent on these other variables Z in a very rich nonlinear way, but that the contrast itself with this function G could be simpler. So it's not uncommon, even modern applications, that F could be a very nonlinear complex function, but G could be something simpler, like a parametric or linear model. So when you decouple things so that the response under an alternative treatment level is actually used across other treatment level responses, make your life easier. Another interpretation of that is you can have this table that you see at the bottom there actually comes from totally different domain. It comes from molecular biology, modeling relationships between gene expression. So X could be gene expression of one particular gene, and Y could be gene expression under a different gene. So you may have, again, knockouts. We're going to delete the possible ways by which a gene can be expressed. So it could knock out gene X, but you have different combinations of X's and Y's. You may want to postulate a template, like, for example, in the bottom left, you have this template where you have only an additive effect once you knock out gene X. You could have this template being applied to different pairs of X and Y's. So each X and Y will have a different beta, different way by which Y responds to X naturally. But this template is shared by different pairs of X's and Y's, and can even share parameters there. This delta that you see there could be shared by different combinations of treatments and outcomes. So in the case of a transport system, you can think about the physical constraints that you have there. So covariates here, for example, could be the state of the system, the moment of disruption. It could be the number of passengers who are inside the system at the moment of the disruption and how long they have been inside the system. And they're going to think about which constraints might be useful, which, at least approximately, which constraints might be useful to formulate these templates. So here's an example of something we did in the past. You think about the expected number of exits that will take place in a disruption as be a modification of the counterfactual number of exits had no disruption taking place. So what I have there is the expected natural number of exits. This is what would have happened if no disruption had taken place. So this would be the counterfactual outcome in that case. So I'm just going to modify it by making up two other features of my system. So you can think in these dashed arrows, a flow of passengers which cannot reach a station SI because the lines are blocked at that moment. But also, there are people who cannot continue past SI. So these are what I call the missing outflow. They cannot continue past SI, so they might leave early at that station. So the missing flow will subtract from the counterfactual. The missing outflow would add the counterfactual. So I can create some generic templates. Here is an example that I'm not going to walk through. It's a bit ugly, but the message that is in there is you see all these features there being functions of the counterfactual distribution. So this missing flow that I mentioned to you is, again, the flow of passengers that you'd have had if no disruption had taken place. You can estimate that from data. You can plug in a regression model and can, by looking at historical data, regress what actually happened against these features of the counterfactual distribution. And then at prediction time, you can play this game again of just taking into account your estimates of the counterfactual distribution, treat them as covariates in a predictive regression model, and then just turn the crank of this prediction machinery to come up with a prediction how many people would exit at different stations. So this is an example of an application to the real case, this Victoria to Brixton station that I mentioned there, where the blue line that you see there is the natural regime, the typical number of exits you see at Victoria Station. There was a period, a peak time from 5:30 to 7:30 where it was disrupted. The average over those 2 hours is shown by this horizontal blue line, which is far off from what actually happened, which is the red line that you see in the same graph. And the black line that you see is just a prediction, out of sample prediction according to this strategy that I mentioned to you. So this is based on the idea that you're using the counterfactual distribution just to generate features which are plugged in a model, and sharing all these parameters over different types of different parts of the system that even though represent different stations and connections, you are postulating that these parameters could be shared among them, which was the case here because this Victoria to Brixton event wasn't in the training set. But under those assumptions, we could carry over what we learn from different disruptions to make a prediction in this case in unseen disruption. So motivated by that, it can be more ambitious, think beyond these handcrafted features and just take them as a proof of concept that they raise information, the counterfactual distribution, to be used as covariates for these transferable disruptions in different parts of the system. So what you see there is a kind of very general formulation of this problem. You had a natural distribution, this P underscore natural there, which is the counterfactual distribution had no disruption taking place. The left side is what would actually take place when a disruption happens. And this side that you see there is just a function mapping one to the other. And it has three parameters fitted. So these parameters are the ones which are shared. At the bottom, you see there just a very simple example what this would mean. So the number of exits, this Y disrupted, the number of exits under disruption, here is postulated to follow a Gaussian distribution with parameters, which themselves are given not by a fixed set of covariates, but for summaries of the counterfactual distribution. So mu natural and sigma square natural are just the means and variances of the counterfactual distribution, which are then plugged in this model. And whatever transformations you make of them are what are going to be learned across a database of past disruptions. So I can make this non-parametric. I'm not going to get into details here. There's a whole literature in machine learning where you represent distributions not only by particular moments, but potentially for infinite number of moments. You can represent them using a trick called kernel mean embedding. It's not of my interest here to describe what it is, but I'm just telling you that you could think in terms of a very large set of expectations of a distribution as a way of representing them. So you could think of this bottom equation there being replaced by something much more general that uses something beyond the mean and the variance of these distributions. Okay, so I'm applying this idea to a data set of actual disruptions along the underground. There are all sorts of practical problems when taking into account here. Many disruptions are very simple, don't have much of an effect. We did some pre-processing to identify which events might be more dramatic, so of more interest. So you could model them directly instead of conflating everybody with a single model. This is based, the way we do this triage to begin with is based on network structure only, so you don't use the counts there. But basically what is in this equation, without going into much detail, is just calculating how many origin destinations will intersect where the disruption took place. So given that the place that the disruption took place is actually input to the prediction model, is not something which is being predicted, you're not really making use of the outcome variable there. So it could potentially just use a network structure to rank which events will be more dramatic. So this graph here shows that this topology only criteria correlates with the actual counts that you observe. So what we show there is there are many events which are in this vertical line under one. These events are just events where the effect was very small. The effect of disruption is very small. And there are events which were more dramatic. These red stars there are those that we picked. They actually correspond to events that the counts were dramatically different. But when you selected them, you only looked at the topology. So you selected these 20 events to fit a non-parametric distribution to distribution regression. We evaluated that as out of the typical out of sample framework. We do cross validation, split the data into 10 folds. then evaluate out of sample how well we did in predicting the number of exits in the disruption. So here, compare against two baselines. They are very simple baselines, partially because there isn't really much out there we could compare to. Because these are different events at every time, you do need some assumptions linking them. So you cannot just fit a black box model to the disrupted data. So you just wanted to see how much would improve, for example, compared to just ignoring the effect, just comparing to a baseline where you use the natural distribution to make predictions. And another model that just randomly perturb parameters of our mapping distribution. So focusing only on the left-hand panel there, this is an evaluation out of sample on how well the predictions fit the actual counts of exits. And the red lines indicate where you actually did, the red stars indicate where we actually did better. So this is indicating there's real value on exploiting a model that runs across disruptions and predicts out of sample for novel disruptions. The way you can represent this more explicitly, I'm going to break here in two sets of examples on what the actual predictions look like, contrasting what our model predicts to what the natural regime predicts when it ignores the disruption. So the first selection are cases where the natural regime was just really bad on matching what happened in reality. So the blue line there represents a model for the natural regime, predicting what the counts would be in that particular time period. And what you see as the black star at the bottom is what the actual count was. So this gets really hard. Many of them were actually went straight down to 0, even though in principle, some people could reach that station. And our model doesn't necessarily do fantastically here, but at least shrinks results towards 0 as you'd expect. So our model is this red line, this orange density that you see there. And this other set of cases that you use to illustrate our results, these are where our model did particularly well. So as you see, our model did well in getting the black dot fairly close to the mode of the distribution, while the natural regime, the blue density that you see, that data is still extremely bad. It got nowhere close to the event that took place. So this was done with very limited data. You only have a few dozen cases of disruptions. We actually, we're actually a bit surprised that such a flexible model is still able to add value to this model, to this problem with limited data. So this incentivizes us to apply that to more complex data sets or more cases. There's something to be done there about measures of uncertainty. That what we provide here is just a point estimate of the model. We may want to also provide measures of uncertainty, especially if we're worried about tail events. So this will be important too to take into account in future work. And some general issues of scalability that those who know about this kind of embedding methods might be worried about. So it's something to take into account too when you're considering these models. All right, so thank you very much.